this, especially after the memory mark. So one of the I want to do this example after the. So every community brain with one has the maximal. That is a simple thing. But the first time I ever saw this theorem, I thought, isn't that kind of easy? Because I mean, you sit down and, almost any range you can think about, you can kind of conjure a maximal ideal, right? If I think of the integers, all I have to do is think of the ideal term by 2. There's maximal ideal. If I think about a polynomial ring over a field in 10 variables, x1 to x10, I can think of my x1 up to x10, right? Let me give you an example that illustrates that this is a non-trivial theorem. Okay. And actually, I'm going to kind of skim over this. I'm going to let you work some of the details. I'll let you go through some of the details. But let me give you the following example. Let R equal the direct product. That's easy. Now, this is a community brain with identity, right? The identity is, of course, the element that has ones in all of the coordinates. So actually, I like this way. This is the set epsilon 1, epsilon 2. For epsilon i's. So I'll index the increase by the actual numbers. Now, let me give you some examples of maximal ideas. Here's some maximal ideas. Okay, let M1 be the collection of all sequences where the first term is 0, and you've got complete freedom in the second coordinate and beyond. Let me point out that this is an ideal, right? Because if you add any two things that begin with 0, you get something that begins with 0, ding, 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 right? And if you multiply this by a sequence, I don't care what it is, when you multiply that first term 0, it becomes 0, and so this actually sucks. It sucks everything, right? Okay, so that's the idea. Anybody want to argue that it's maximal? And in fact, it's maximal. Let me give you something a little fast and loose, and then I'll give you something a little. What happens? What do you suppose happens when you take R and you quotient out by M1? You essentially get the first coordinate, which is C2, which is field, so this is maximal. Let me give you another argument. Suppose alpha 1, alpha 2 is not in. So alpha 1 is equal to what? If it's not an M1, yeah, if it's not an M1, then alpha 1 has anybody unsure of that. Let me point out that 1, alpha 2, alpha 3 plus 0, alpha 2 plus 1, alpha 3 plus 1 equal to 1, 1, right? So that means, and notice that this thing right here is M1. So in other words, if you look at M1 and you join this element to it and try to generate a larger ideal, you automatically get the whole thing. Because throw in any element that starts with 1, just pick the first coordinate to be 0, and basically what you're doing is picking the opposite of this. If alpha 2 is 1, and this is 0, if alpha 2 is 0, and this is 1, this element's always an M, so that means that when you throw this into this ideal, you get it. Agreed? Okay, so far. Okay, well, there's nothing special about this being the first coordinate 0, right? So let me give you a larger list of maximal ideals. These are all maximal ideals, right? 0 on the first coordinate, freedom everywhere else, 0 on the second coordinate, freedom everywhere else. These are all maximal ideals. Now, here's a $64,000 question. Is that it? Is this an exhaustive list of maximal ideals? It is not. But I challenge you to find any other one. Let me illustrate why this bread and butter is so, it's not non-trivial. Consider the following idea. This set sequences on n, 0. Let me clarify that. This n is not fixed, it can vary. Remember what the direct sum is, well, not in general, but the direct sum in this particular case are all things that are eventually 0, right? Notice this is also an ideal, right? Because what happens if I add up 2 of these things that end in an infinite tail of zeros, I get something new that ends up in an infinite tail of zeros. Do I agree with that? What happens when I take anything in the ring and multiply it by something that ends in an infinite tail of zeros? I get something that ends in an infinite tail of 0. Right? Now, this theorem says that this ideal is contained in a maximal ideal. But none of those. Right? Because, right. For example, this is not contained in M1 because certainly the element 1, 0, 0, 0, 0, 0 forever is in here, but it's not in M1. The element 0, 1, 0, 0, 0, 0, 0 is in that direct sum, but it's not in M2, and so forth and so on. Describe the maximal ideal as M. It is in fact not a maximal ideal, right? And in fact, anybody explain why it's not a maximal ideal? Maybe I'll take a quick step or two on this. Yes.
Oh, you could have shown, you could add an element that's got infinite many non-zeros and infinite many zeros.
So for example, I could take that element that alternates 1s and 0s, that is not in the direct sum because it doesn't end in a string of zeros. Now I can adjoin that to I, but it is impossible for there to be something in the direct sum plus something here that equals the string of all ones. That's a fairly easy computation to show. So this is not enough. This is not a maximal. Is this a maximal ideal? Well, no, it's not even. So now maybe I want to stick on something that like has some different. And all of a sudden, I start to realize that, in fact, you have to make many choices to specify maximal. In fact, the direct sum is contained in the maximal ideals. And which one you want to say it's in is governed by your choices here. I chose 0, 1, 1, 0, 1, 0, 1, 0. I could have chosen 0, 1, 0, 1, 0, 1, etc., right? Because see, now that I've made this choice, I can now, for the next step, to try to do a maximal ideal, I can't put in 0, 1, 0, 1, 0, 1, can I? Because that plus that would equal 1. So when I make this choice, it eliminates future choices. There is a maximal ideal that I is contained in. There are infinitely many maximal ideals that I is contained in, but they're governed by the choices that you make. And I challenge you to write any of them down. You're just not going to be able to do it. So this theorem, despite the fact its consequences seem trivial in rooms like, polynomial rings over a field or the integers, actually a highly non-trivial result and does depend on choice. Any questions? Yes.
Can you prove that you have to join infinitely many elements to find a maximal ideal that contains this ideal?
Well, let's see if you can. I mean, I'll put that on the homework.
I don't mean like right now. I just wonder if you knew if that was the case.
I would think that probably could do something like that, right? And I suspect that there might be an inductive argument, or I suspect that there may be, but I'm not sure. But yeah, I promise you, you're gonna have to make a lot of choices. Any questions on that? Okay, so the last thing we talked about was primes versus irreducibles. And the last thing I'll prove is if you have a non-zero prime in the domain, then it's irreducible. Right? Let's look at some examples to kind of contrast these notions here. I'm going to start with something that many of you may have seen in your different travels. This is kind of a class. How do you factor 6 in this range? Oh, you didn't answer fast enough. I'll get that easy. Anybody say no way factor 6?
Conjugate pair 1 plus root -5 times 1 minus root -5.
Excellent. Now, it turns out that 2, 3, and 1 plus or minus radical -5 are irreducible and not prime. And in fact, let me point out that, for example, with 2, notice that 2 divides this product here because it divides 6. But 2 divides neither this nor this because there is no 1/2 plus 1/2 radical in this. Same with 4. Everybody else doing it? What's missing from my argument a little bit? I think I convinced you all that 2 and 3 are not prime, but what perhaps is missing? You actually have to complete this, to make this a complete argument, you need to show that these are all in fact irreducible. And How many of you have ever seen this? If you've seen this in the context of number theory before, you've probably seen norms. You can make these kind of arguments to show that these are irreducible. I don't expect you to know that yet, and if we get to it, I'll sort of spell that a little more. You can use norms. You can also brute force the argument that these are irreducible by playing around with the elements of the ring. Let me give you an example that I think let me give you an example, something I think is kind of nicer. Okay, what is this? Well, this is the set of alpha 0, alpha 2, alpha 3. Okay, so let me put this more simply. This is basically polynomials where the linear term is absent, right? So the coefficient of the linear term, the degree 1 term is always 0. Notice that this is an honest to goodness ring, because what happens if you add two polynomials that are missing the linear term? New polynomial missing the linear term. What happens if you multiply two polynomials together that have no linear term? It doesn't like spontaneously generate, right? There's no way to do it. So this, and in fact, since it's a subring of the polynomial, the full polynomial ring, it's an integral domain. Let me show you some irreducibles on prime. Notice that take the element x to 6, that's in here. This is kind of cool. Notice that x squared is irreducible. Let me make that argument. Let's suppose that x squared can be factored into two things, non-trivial, right? The degree of x squared is 2. And so if I have it break down into two factors, what are my choices on degree? 0, 2, that's one choice. And tell me why that one's junk. That's right, degree 0 polynomial in this ring is a unit, right? Because it's over field. Okay, so my only other way to break it down is 1 and 1. And look at my cheating self, right? There's no ones to do at all, right? You have a similar problem with 3. 3 is also irreducible. Because how can you break down 3? Well, 3 can go degree 0, degree 3, and that's junk because that. And no matter how you cut the cake after that, there has to be a degree 1 factor, which isn't there. Right? So these are honest. That's a little easier, I think, to see even in the norm. And these two are irreducible, but not prime, because notice x squared divides the product of these two, but it doesn't divide either one because there's no linear. X cubed divides the product of these three and doesn't divide either one because the degree is all wrong. Am I agree? Let me give you one more example. This is the set of Q0 plus alpha 1 x plus alpha 2 squared, alpha 2 x squared, alpha 5 Q0 fractional. Okay, so these are just like real polynomials, just like you were in like a high school algebra course, except I've got one little caveat. I demand that the constant term be a rational number. Right, okay? If instead of Q here, I had all the real numbers, X would actually be a prime element. In this situation, X is irreducible, but not prime. It's fairly easy to see that X is irreducible. The same kind of argument we did before. It's degree 1. And the only way you can break that down is degree 0, 3. So no choice, it's irreducible. But it's not prime. Because notice I have these two exotic ways to factor X squared, right? Because once you're up with the degree of X, with the power of X being at least 1, you have any freedom for real numbers. So for example, where pi is the real pi, real number pi. Notice that X divides the product of these two because the product of those two is squared, but it doesn't divide either element of the product because to divide either one of these, you need either pi or 1 over pi to be in that ring, which it ain't. Everybody okay with me? Actually, it's interesting, so I'll point out just for fun, the element in this ring, the element X squared, has uncountably many different factorizations, but they're all of length 2. Right? No matter, there's uncountably many ways to do it, but they all have exactly 2 factors in factorization. Let me make this worse. Make it worse. Now X isn't even irreducible. In fact, it can't even be factored in irreducibles. Anybody see what the difference is? Remember, in my last argument, I said, well, look, X is irreducible because take X, if you factor down, one of those has to be degree 0, therefore it's a unit. Not the case anymore. Because yes, factor X, one of the factors has to be at degree 0, but it doesn't have to be a unit. All right. So for example, X is 2 times X over 2, which is 2 times 2 times X over 4, which for all n is 2 to the n times X over 2 to the n. In fact, no matter how you juggle this around, you can always pull yet another degree 0 factor out of it. Not only is X not irreducible, it can't even be factored into irreducibles at all. Okay. Any questions? Let me give one more example. Long design, and some of this might be for the number theory junkies in, but I can actually, yeah, I'll give you another 2 examples here. One of them might have to wait for a second, but I'll go ahead and do it. Okay, so I haven't proved this hardcore, but maybe it's sort of believable that X can be factored into irreducibles, right? Because the only thing that you can try to, first of all, X itself isn't irreducible because there we go, breaks down. And for x to factor into irreducibles, there would have to be a degree one piece and a bunch of degree zero pieces, right? But no matter what degree one piece you have left over, you can still pull more degree zero pieces out. So here, it looks like x can't be factored into irreducibles at all, but some things can. For example, 2, right? 2 over. Anybody give me an example of an integral domain where nothing can be factored into irreducibles? So such an integral domain could have no irreducibles at all. I'm waiting for the smart aleck response. Somebody get me over the hump with the smart aleck response. A field, thank you. I knew I could count on you. So yes, a field is a great example. Okay, so now let me add in a caveat on where there are no irreducibles whatsoever. Not even 2. And both of them might require a little machinery, but hopefully I can put this in your tool belt. You can kind of get it. So one is the ring of all algebraic numbers. And let me tell you what I mean by this. This is the collection of all complex numbers such that Z is a root of a mnemonic polynomial. Okay, so we're going to see later that such constructions here always form rings. It may not, at this early juncture, it may not be clear that this is a ring at all, right? Here's the problem that comes to my mind. Suppose that you have Z1 and it's a root of P1. And now you have Z2 and it's a root of P2. Is it clear that Z1 plus Z2 is the root of some other mnemonic polynomial? I don't think so, right? It doesn't seem clear at all to me. It's not even clear that the product is the root of another mnemonic polynomial. So this is actually a sophisticated thing, but you know, hear me now and believe me later. This actually does form a ring, and we'll show you later why this is true. What's in here? Well, for example, all integers are in here, right? But so is more exotic stuff. Square root of 2, 1 plus radical negative 19 over 2, all 5 complex roots of x to the 5th plus x plus 1. Anything that any mnemonic polynomial on this actually has no irreducibles at all. Anybody know why? Let's suppose. Let's say x to the n plus m to the n minus 1, x to the n minus 1, m 1x. Suppose alpha is the root of that. That's what it means to be in membership here. Oh, by the way, my subscripted m's are all here. If alpha is a root of this, so you plug in alpha, you get 0. What can you say about this polynomial? Okay. Square root of alpha is a root of this. And actually, I could have done the same thing by replacing x by x cubed and get the cube root. Right? suppose alpha is irreducible. But radical alpha is in, C bar as well. And alpha and there's a contradiction, because if alpha is irreducible, then radical alpha has to be a unit, but if radical alpha is a unit, so is alpha. Right? So this thing contains no irreducibles at all. And I think I'll pull my other localizations. Any questions on it? Okay. Multiplicatively closed sets and local. You might have seen some of this depending on where you saw your 8510 or maybe not, but we'll get you through it anyway. So the idea behind multiplicative sets and localization is this is sort of the idea of forming fractions, right? But it actually goes deeper than that because there's a very intimate kind of neat connection between multiplicatively closed sets and prime ideals. So let me start off. So definitions. Okay. What are the one? A set S and R usually zero since they're not an element of S. Is said to be multiplicatively closed if I think this definition is what you would expect. Multiplicatively closed means I have two things in there. They're probably still in there. Of course, in general, for a multiplicatively closed set, we don't expect it to be additive. Continuing with this definition. We say the multiplicatively closed set S is saturated if ST and S plus S. Okay, so let me make a couple of notes about that part of the definition. I put multiplicatively closed in parentheses there because there's no real reason that you need multiplicatively closed in the definition of saturated. However, if you're reading something, most authors assume that the saturated set is already multiplicatively closed. Multiplicatively closed means it contains products. Saturated means it contains all its divisors, right? Here, S and T are not assumed to be an S like they were in the first. S and T are in R. Maybe I should add this here. Clarity. So in particular, Any saturated set must contain. If it contains all its divisors, it has to contain one. And in fact, from that, it actually has to contain all the units as well. Notice this is a little anti-symmetric, but notice this also implies that it contains T as well. Okay. So, for example, let me give you an example here too. Is multiple close. Right, powers of 2 multiple close. Actually use the powers of 2. One more. Notice this is not saturated. Right, because in particular contain units. Notice that plus or minus 1, plus or minus 2, plus or minus 4. I'm saying is saturated. And multiple close. Let me point out that that second set is the smallest multiplicatively closed set that contains the original, but is also saturated. One way that you can always take a multiplicatively closed set and saturate it by throwing in all the divisors, things that you find there. Notice this is in Z. They're also in Z. The set of odd numbers is saturated and multiple closed. It's clearly multiplicatively closed. It's the product of 2 odds is odd, so no problem there. And if the product of 2 things is odd, neither one of those things can be even, right? So it's saturated as well. Okay, we have a multiplicatively closed set that's not saturated. A couple of saturated sets. Can anybody name the saturated set that's not multiplicatively closed? This one. Useful.
Plus or minus 5.
Yeah, that's right. That's a good set. So I'll put that one in there too. That set certainly contains all its divisors, but it's not multiplicatively closed because, not even 6. Let me do another one here. Start here. See if you guys pick up the pattern. Does anybody know where I got this number? That's right. This is basically everything that's not a multiple six, right? That's what I'm trying to pull off. Notice that this is not multiple closed because 2 and 3 are in there. Those products. However, if you look at the saturation, look at any element here, right? The divisors 2 are in here, the divisors 3, the divisors 4, the divisors 8, 9, and so forth, right? Because there aren't any multiples of 6, you don't have to worry about it. So this is kind of another interesting example on those on the scale. Here is a big theorem. I'm going to call this 142. Let R be commutative of identity and I an ideal. If S in R is a multiplicative set such that I intersect S is empty, then there is a prime ideal such that this is a terribly important theorem, actually. Let me kind of draw you a picture of what's going on here. Yeah, I can't believe I want to draw pictures in a rainberry class. I feel dirty as apologies, but I'm going to do it anyway. So here's what the theorem says. Suppose you have this large oval shaped ring and you have an ideal in I, and you have a multiplicatively closed set S. And the hypothesis is I and S don't overlap. They miss each other. And what you can do is sprinkle a little bit of manure and water on I and grow it to a prime ideal P that misses S. So you can expand I out to a prime P that still misses S. Right? This is actually a very useful, and this will come up many times. This is very useful kind of result. First thing is, you claim that there's this maximal with respect to the property that P what is this? Where does it smell like I'm going here? Yeah, it sounds like Zorn, doesn't it, right? So I claim the first step in this proof is I claim that if you start off with an ideal I, then this S, you can expand it to another ideal, we'll call it P, that is maximal with respect to the property of missing S. Notice that if I is already maximal with respect to the property, we're done. So as indicated, I think this is Zorn going on here. So let's let gamma be a set of ideals J such that and J intersect S is equals. Okay, so notice that this is a coset under including let me make clear this is not ideal. J for ideal, of course. Notice that this is partially ordered set under inclusion. So to utilize Zorn's lemma, what we've got to do is we've got to show that every chain has an upper bound. So let's let C taking, I think these are very similar to before, be a chain. Gamma, that is for all alpha, beta in our index set. J alpha is contained in J beta or the other way. One of these two ways. Now, let U be the union of this chain. As before, this is remember, I said that it's often a hazard to look at unions of ideals and expect to be ideals because they're usually not even close under addition. However, the chain saves our butts here because the chain, these ideals are sort of expanding out in a certain sense, and U is actually a bona fide ideal. And let me also point out, U contains I, good for us, and U intersect S in because if there's something in U and in S, it has to pick it up in one of these unions. I love unions for that property, right? And if it picked it up in the union, it has to pick it up in one of these J alphas, which was supposed to have an empty intersection with S. Everybody cool? So by Zorn, there exists a maximal element. We call it P in gamma. So that is to say, P contains I and P is maximal. Now be careful here. When I say maximal, I don't mean necessarily that it's maximal ideal. I just mean it's maximal with respect to the property. So if X is not in P, then the ideal generated by P and X. So if you just increase this ideal by a little bit, by adding X to it, intersect S, it's not in. So if you grow P just a little bit, it'll pick up, it's guaranteed to pick up something from else. So we've got most of that licked. We now know that there exists an ideal that is maximal with respect to this CS. The next move in the chess game show that this P is prime. Any questions? Actually, you want to think about why that's true. It's kind of a cute little thing. Any questions? All right. I'll see you all on Wednesday. I did remember the report. See you later, Colin.